Today we are going to talk about how we can use these redox reactions and harness their energy. And you guys already know this because it's a battery. You have it in your phone, you use it in all kinds of things. And what we're doing is we're harnessing that flow of electrons. Remember, a redox reaction is something that gains and loses electrons. So we harness this by making a voltaic or a galvanic cell. So they're called either one. They're called a voltaic cell or a galvanic cell. And what we do is we separate these half reactions. We've been writing half reactions and we separate them. We connect them with a wire and then we can run it through a voltmeter so we can see how much energy we're harnessing. So let's just go through what this cell looks like in some of the vocabulary. First of all, this is a metal electrode, and this is a metal electrode. So we have reactions with copper and zinc, and one of these would be oxidized. That would be zinc. And anode is where oxidation happens, and that's the loss of electrons, okay? If our other half reaction was with copper and copper ions, zinc is higher on that activity chart than copper, so zinc is where the oxidation happens. It's called the anode, and cathode is where reduction occurs. So here my metal is going to lose those electrons. It's going to flow through this wire. Now if a zinc little atom here loses an electron, it comes off as a zinc 2+ ion. Okay, so these atoms start coming off this anode and turning into ions. Ions will dissolve in solution and this metal won't. So this anode starts slowly going away. Now electrons flow into the cathode and we have a solution that contains copper ions in there. And the copper ion will grab this electron and it'll plate on as copper metal. And when a metal goes on to another piece of metal, we call that plating. So a cathode is where reduction occurs. It gains that electrons. That's where my metal ions turn into the solid metal. And I like to remember this as CRAP. Cathode, reduction, and product. Here I'm making that solid product on this cathode. Anox and oxidation. Okay, so anox makes CRAP. You can remember it that way. Now, the one thing I didn't talk about is the salt bridge. So if I keep building up negative charges here, let's just think about this like a magnet. If I get too many negatives here, this negative electron won't want to come, and sooner or later my voltaic cell will stop working. So we make this salt bridge, and let's call this guy potassium chloride. Okay, and they're a bunch of ions. So we have potassium ions, and chloride ions, and chloride ions. And what happens is my negative flow goes this way. It keeps going this way, okay? So the salt bridge helps the negative flow by my chlorines keeping that negative flowing in that circle, which means my potassium would have to be flowing in the opposite direction. So let's do an example. Okay. So in my example here, I have zinc is turning into zinc ions, and iron ions is turning into iron metal. So the first thing I have to do is I have to find zinc and iron, and I have to decide which one's going to oxidize, and oxidation happens at the anode, anox. So zinc is oxidized. So just because out of habit, I'm going to put zinc here, and I'm going to call that my anode because we're losing the electrons. And I'm going to put my iron over here and call that the cathode. Now remember, these are beakers. It could flip, so my anode could be there and everything could be running this way. But IU usually puts it this way with my anode on the left. So just a standard procedure, I'm going to put it there. Okay, so what's going to happen at the anode? Well, we're going to lose those electrons. Okay, anode is oxidation, and that means my zinc's going to come off and it's going to form zinc 2 plus ions. Now, we have iron already in solution for us, and we have these electrons here. Okay, so my zinc is going to grab that electron and it's going to plate on, my iron is going to grab those electrons and it is going to plate on as iron. We have iron in solution there. And so cathode is where our reduction happens. Cathode, reduction, and product. We're making that metal there. And reduction is gain of electrons. So we're gaining their electrons. Oxidation is loss. Here's my oxidation. So anode oxidation, cathode reduction. And so my flow of electrons is going from the anode to the cathode. Okay, we can see that. And then I have these half reactions. What is happening just on this side? This is where those half reactions come in that we looked for. We have zinc is going to a zinc 2 plus, and it lost the electron, so my electrons come off at the end. My half reaction on my cathode side is we have iron 2 plus, and it's gaining those 2 electrons to make iron metal. Okay, now my salt bridge flow. I am going to put it upside down here so you can see how the salt bridge just makes this lovely loop. Okay, so we have negative ions there, and my salt is sodium and nitrate. This goes here, which means my negatives keep flowing here. So nitrate is going to keep the negative flowing in the same direction, which means the positive sodium is going to flow this way. Okay, so when you look at it upside down, you see it's just this big negative circle loop where electrons and negative ions just keep flowing around in a circle. So I think that's easier to see the flow if we do it upside down. They draw it like this because this is actually how it looks in the lab. So our salt bridge flow, we have NO3 plus to the anode, and we have sodium, NO3 minus to the anode, sodium to the cathode. Okay, now there's something called the cell annotation, and basically we have the anode side, just like I do here, anode, double line, cathode, and you don't need to write these words, I'm just putting there so you know. And instead of writing this out like this, what they do is they say zinc goes to a zinc 2 plus, and iron 2 plus goes to iron, and that's a cell shorthand notation or cell annotation. Okay, so the other thing to know is my anode is losing mass, and you can see that my zinc metal is going off, it's dissolving into ions in solution, and then my iron's plating on, so my anode is losing mass. And here we have on my anode side, and my cathode is gaining mass. So if you can draw this out, you've got a pretty good hand on electrochem. So in your book, they show you a lovely little picture, which I want to go over. This goes over all my notes. We have our zinc anode right here, and this is a copper cathode, and they show you a very close-up view. There we go. Of the zinc coming off into solution, and here's my zinc coming off into solution, okay? And then they also show a close-up of the copper, and the copper starts plating on. And here's actually what a real electrode looks like. You can see the zinc anode is dissolving, And the copper cathode has all this crap on it, which is the copper. That's why I like to use CRAP, cathode reduction and product. Okay, and there's a lot of little close-ups here. And here is another close-up of this half cell notation. Zinc solid goes to zinc 2+ aqueous, and copper aqueous goes to copper solid. And you know, I didn't put my state symbols in, so let's go back and put them in. So we have our zinc solid goes to zinc aqueous, and iron, that is my ion that is in the aqueous solution, and it turns into iron solid. There, that completes that half cell notation more completely.